Okay, I think we'll go ahead and get started. And I want to thank y'all for coming out today. This is being recorded live for future generations if they happen to decide they would like this information. So we have a little bit different format than we would typically use. We will be having short segments, about 20 minutes or less, before we take a short break. And so I'm going to depend on you to take short breaks in order for us to finish on time. So we have several 5-minute breaks put into this presentation. And because it's being recorded, I do want to take your questions, but what we will do is at the end of each little short segment, we'll have an opportunity for some questions. So if you can hold them until the end before we take the break, then we'll have an opportunity if you come up with any questions. And with that, I want to thank you again for coming to this decision tree training for remediation of chlorinated solvents in groundwater. First of all, I'm going to introduce the topic to you and talk about innovative groundwater remediation in South Carolina. I'm also going to cover the principles behind the decision tree, because if you understand the principles, the decision tree is sort of secondary once you understand how it's set up. Then I will get into the components of the decision tree, which include covering active technologies, passive technologies, pilot studies, and monitoring recommendations, and this is all for chlorinated solvents in groundwater. We do have a few little practical exercises interspersed, and then at the end there will be another practical exercise. And again, at the very end, if there's any discussion or comments, we'll be glad to have that also. And before I get started, I wanted to go over some key terms. So the first term is ERD, which is enhanced reductive dechlorination. Some folks also know it as in situ bioremediation. ORP is one of the key components of what we'll be talking about with respect to geochemistry. That's oxidation reduction potential. An example of ORP is if something is positive, has a positive ORP, you put a nail in that water with a positive ORP and you're going to get rust. If you have a negative ORP and you put a nail in that water, it's going to turn black. ISCO or ISCO is in situ chemical oxidation. DO is dissolved oxygen. PRB, permeable reactive barrier. ZVI and NZVI are zero valent iron and nanoscale zero valent iron. ERH is electrical resistance heating. MNA, monitored natural attenuation. Phyto is what I use for phytoremediation, just to save on the syllables, save my breath. ISCR is in situ chemical reduction. That is very similar to zero valent iron for the purposes of this talk. They're sort of equivalent, although there are other ways to reduce groundwater chemistry. DPT, direct push technology, and DNAPL, dense non-aqueous phase liquids. And so now I'm going to talk about the information I pulled together on innovative groundwater remediation in South Carolina, which is why I actually put this decision tree together. So a number of years ago, I was looking at innovative technologies in South Carolina, and I was wondering, how are they doing? It'd been long enough that a lot of those innovative technologies had been implemented, had monitoring results, and I was curious, are they working? Our expectation is these are the greatest things since sliced bread, and of course they're working. They're going to solve our problems. I mean, the innovative stuff is really cool. So I evaluated 126 sites that were managed by state and federal Superfund, RCRA, and above ground storage tank sites. And all of these sites had innovative technologies, and of the 126 sites, 100 of them were chlorinated solvent sites. I reviewed the files for all of them, and the ones that I found particularly interesting or different, I wrote some site summaries and lessons learned for each of those sites, and that was about 52 of the sites. So after I did my file review, I talked with the technical staff. If there was somebody that was a project manager on the site, I talked with them to confirm if my observations were correct. And I found that there were a number of lessons learned, but I didn't see that they were being shared from one consulting firm to another, or from one person to another within a firm, or within our agency. I didn't see that they were being shared. And so I wanted to confirm some of these lessons learned were actually in the literature, because it didn't seem like it was being shared. So this is the breakdown for the number of sites that I looked at for the different technologies. I looked at 39 sites with reductive dechlorination, 35 ISCO sites, 8 PRBs, 7 phytoremediation sites, 5 recirculation wells, 4 thermal sites, and 3 zero-valent iron sites. There are a number of successes and there are a number of failures. Many lessons to be learned. And after I looked at these 100 chlorinated solvent technologies, I concluded that I think we can improve the success of our technology selection and how we implement and monitor. Only 30% of those innovative technologies were expected to succeed. And when I say expected to succeed, it means they made significant progress towards meeting their goals, and it was expected that they would meet their goals in the future. And this was something that I confirmed with the project managers. So why are we having, or at this point in time, why were we having this amount of difficulty? Some of it was site characterization issues. If your site is not characterized, you can go out and put in a remedy, and all of a sudden you're not making progress towards your goal because you missed an area. Some of these projects did not even have a pilot study that maybe needed one, especially for innovative technologies. Pilot studies are sometimes helpful. Or if they did a pilot study, it was just not properly designed to achieve the objectives. A lot of assumptions were made of, oh, we can inject this technology and we're going to get a radius of influence of blankety blank feet, and without any data to support that. One of the biggies and one of the key parts of the chlorinated solvent decision tree is the aquifer geochemistry was not compatible with the remedy. And there were some monitoring problems. Sometimes all you need are some basic indicator parameters, and they'll tell you, are you having an effect? Is your technology affecting groundwater? And those are fairly cheap and inexpensive, and they give you quick information. And sometimes these projects that didn't succeed were not checking the basic indicator parameters, and they might have waited a year to send us a report on how they were doing. So by the time we find out, oh my goodness, things aren't doing what we were hoping, it's already been a year, and it's very difficult to go back and make corrections. And then sometimes the monitoring points were just like, 5-year travel time. They're 5 years away from where the technology is being implemented, and that really doesn't help us understand how it's doing. So I've probably emphasized this to you 55 times already, but lessons learned, not shared. This really concerned me, that in these files we had this information that we were learning, but it was not being broadcast. So that's why the chlorinated solvent decision tree was actually developed. It was to allow the lessons learned to be transferred and used in the selection of a remedy for chlorinated solvents in groundwater. This is my summary of the lessons learned with a potential approach to address chlorinated solvents in groundwater. I'm going to talk a little bit about the lessons learned up front, and then you'll see how those are worked into the decision tree itself. The first big category was geochemistry. And then we also have lithology, and time frames are part of the lessons that we were learning. For geochemistry, the remediation effectiveness often depended on the similarity of subsurface geochemistry and technology geochemistry. Where we really run into problems is when your technology has a different chemistry than the aquifer, significantly different. If your pH is significantly different, your oxidation reduction potential is significantly different, then you run into some problems. One of the big things that happens when you have a contrast in geochemistry is fouling. Fouling can occur as a chemical precipitate. We've had some experience with that. You can also have biological growth, and typically you find fouling where there is a significant change in geochemistry. It can occur within an aquifer, it can occur within a well screen, and if you have a permeable reactive barrier, it can occur at the interface between the permeable reactive barrier and the subsurface. So this is a diagram showing all of the different types of biological materials that can occur in the subsurface and cause problems. On the left is something called EH, which is very similar to ORP. And the top part is oxidizing and the bottom part is reducing. And we can have iron-related bacteria. HAB is heterotrophic anaerobic bacteria. It likes to grow where there's a contrast, where you have both aerobic and anaerobic conditions intermixing. Then we have sulfate-reducing bacteria, denitrifying bacteria, and methane-producing bacteria as you go deeper in become more reducing. So what does fouling actually look like, and how can you actually see it? This is a diagram that shows different scenarios of fouling. The upper left-hand corner is what we would have if there was no fouling, and the blue dashed line is the water level, and P1 and P2 are water level piezometers, and EW is an extraction well. So upper left, that's what you expect to see, a nice cone of depression around the extraction well. If you have fouling right at the extraction well, which is the upper right-hand corner, you're going to have a big drop in your water levels because water is not going to be able to get into that well. The bottom left is when you have fouling in the aquifer close to the extraction well. The actual excessive drawdown actually occurs in one of the piezometers. And then the worst, absolute worst scenario I can think of is the bottom right-hand corner, which is what we really want to stay away from, which is fouling throughout the aquifer, and it just gives you all kinds of crazy water levels. So why does fouling actually matter? It affects the effect of the injection and extraction wells can be changed significantly if you have a fouling problem. If you're doing injection in a permanent monitoring point and you have chemical precipitate occurring, at some point you're not going to be able to inject into that well anymore. You're going to have daylighting. It's not going to have the desired effect. With a permeable reactive barrier, we had a site in Charleston where we, under the direction of the responsible party group, we implemented a technology that we knew the chemistry was not there. It was a sulfuric acid type plume, and they had a calcium carbonate permeable reactive barrier they wanted us to try, and we had instantaneous fouling when that PRB was put in because it formed gypsum, just simple basic chemical equation. Fouling also can affect your monitoring well representativeness. If you have a lot of fouling right around the well screen, then the contamination may be in the aquifer, but as it passes through that biofilm, it's going to be cleaned up. It's going to look like you don't have a problem. And the really big thing about fouling, and this is historical, that everyone knows is you can actually lose an extraction well. And extraction wells can be pretty expensive to replace. I have a site where they're having to replace one, and it's a $30,000 replacement. You can do treatment for fouling, but you have to be aggressive about it. You have to look for it. You have to continue to treat the wells for fouling. So there is a simple and inexpensive way to test for fouling. It's called the biological activity response test or reaction test. You can actually see what kind of bugs you have, and it's a fairly inexpensive test, like $10, $20 a sample. For conventional sampling, you can just look at how much drawdown is occurring and how fast the groundwater well recovers. And certainly with extraction wells, you can just watch the pumping rates and the water levels and see, are you seeing a gradual decline in the pumping rates? Are you seeing a gradual decline in the water levels? If yes, you may need to look for fouling. And in this case, you can look perhaps in a downhole camera. You can remove the pump and look at it. But I think the BART testing is a good way to tell you how prolific is the population. It will, not only will it tell you whether it's there or not, but it will give you an idea of how bad it is. So these are the types of BART testing that you can do, or the types you can test for. And, the first top three are really the ones that I typically look for, but if you think you might have some of the other ones, they can also be tested. So there are some ways to avoid fouling. I call it preemptive solutions. Don't try to change the oxidation state of the aquifer or the pH. If you avoid those two things, you're going to cut back on the amount of fouling. If you do have a contrast in pH, oxidation state, or dissolved oxygen, if you think that's going to happen, you can just use simple basic chemistry like we did at the Stoller site, where we knew we were going to get gypsum. It was a guarantee, calcium sulfate. You can do those chemical equations. It's fairly simple to do, and it can save a lot of grief. And pilot studies are helpful. If you think there could be a problem with fouling, instead of fouling the entire aquifer across the site, just pick a small area to foul. Well rehabilitation is one of the ways we address fouling in extraction wells, and there are a number of procedures out there for addressing extraction wells. If you're going to do injections, one way to avoid fouling is using direct push. But still, if you have that chemical precipitate, it may limit how much actually gets into the aquifer. And looking at alternate technologies, if you can find one that has a better chemistry for the site. There are some helpful websites about fouling, and I believe this presentation will be available. So if you want to look these references up later, then they will be available to you. And at this point, we're going to take a 5-minute break, but first I'll see if anybody has any questions up to this point. Yes? Sure. So a lot of times we find like calcium carbonate. You can look at alkalinity and some basic indicator parameters like that, compare it to other wells in the area. If you have a really high alkalinity, really high calcium, really high iron, those kinds of things, that helps. Okay, I brought my watch so I could actually, or my clock, so I could actually tell 1:22, 5 minutes, and we'll meet back at 1:27. Thank you. 1 minute warning. Okay, it's been 5 minutes, so I'm going to start back. So the question asked at the end of the last session, I will be repeating questions from now on. And the question was, other than biological, is there a way to check for chemical fouling? And so my answer was looking for calcium carbonate, dissolved calcium, alkalinity, those types of things that we typically associate with fouling. So the next group of lessons learned when I looked at innovative technologies in South Carolina was lithology. It plays a key role in the success of some of these technologies or failure. Clay layers and lenses, very common across South Carolina. They reduce permeability. They can affect how much you can inject in the subsurface, and they can prevent the injectate from reaching the subsurface. They can improve the electrical conductance, which is a good thing if you're looking at a thermal technology. Sorption and back diffusion. So clay typically will absorb chlorinated solvents. It likes them, they like each other, and it will hold on to them until the groundwater starts going down in concentration, and then the clay will start to release contamination into the aquifer, which makes it very difficult to achieve your remedial goals. There are, as I mentioned, some technologies where clay is actually helpful. If you're doing a thermal technology like resistance heating or thermal wells, the clay does really well in conducting heat and conducting an electrical current. What can you do if you've got clay? One thing you can do is frack it, try to fracture it up so that you can work through it. You can try to avoid clay. If you know exactly where it is, you can try to inject underneath it if the problem is underneath it. I like soil mixing, which you can do down to a depth of about 22 feet. If your amendment is something that you think will work, you can actually just grind through the clay and get your amendment in there and bust up the permeability and solve the problem. And then, as I said, thermal remedies are another approach. So there are some time frame lessons learned. What is a time frame? Just a general estimate of how long something is going to take. You think of it in terms of weeks to months, months to years, years to decades, decades to centuries. Some sites come up with 100 years. It's going to take us 100 years to get there. So that's what a time frame is. And the thing that really messes up your estimate of how long it's going to take is that back diffusion, which I mentioned before, the contamination coming out of the clays, as well as rebound. It's difficult to know exactly how that is going to happen and what that's going to look like. It makes it a little difficult to design a remediation system. It may be associated with the technology that you are using. In situ chemical oxidation, a lot of times we see rebound from that, and my theory is that when you inject the oxidant, it actually creates a mound, causes the contamination to move away from the injection point, and then as things return to normal, the contamination comes back. Identification of back diffusion and rebound during a pilot study will really go a long way in helping you with your remedial design. Typically, we expect thermal technologies to be the fastest way to get contamination out of the ground. They also happen to be the most expensive. Monitored natural attenuation and phytoremediation, they are the ones that take 100 years or a long period of time. And as I said, asymptotic conditions, when you get down to a certain point and it just won't go any lower, that really makes it difficult to estimate. Are we talking decades? Are we talking 50 years? If we don't really have a feel on back diffusion, we're not going to really know for sure. I have seen some facilities use computer modeling to help them estimate timeframes. Computer modeling is only as good as the data that goes in there. And y'all have had great experiences, we all have, with their wonderful modeling of weather where they have millions of data points and told us the hurricane was going to come to South Carolina. So if they can't do it with air in 1,000,000 points, I have some hesitation about how much we can do with groundwater. Certainly, if you are going to do modeling, I do recommend verification of the modeling with water quality information. So get your model to say 2 years from now there's going to be 10 parts per million PCE in this well, and verify it. So how can you improve the time frame? How you can get things to go faster? Get the source out of the ground. If there's any way to dig it up, then that's going to give you a lot of bang for your buck. For permeable reactive barriers, if you add extra ones throughout the plume, you don't have to put one just at the end of the plume. You can put them in the middle. You can put 3 or 4, depending on the size of the plume, and that's going to speed up how fast your groundwater cleanup will be. In situ chemical oxidation, enhanced reductive dechlorination or chemical reduction, reduce spacing between your injection points. The further apart they are, the further apart the lines of injection points are, the longer it's going to take. With thermal remedies, if you extend the heating time, sometimes you can get a good recovery for that. Typically, thermal technologies run until you reach a point where the vapors show that you're only getting a few pounds out of the ground in a month. So it's sort of a judgment call as to what the cost benefit is of continuing to run a thermal system. But if you're getting 5 pounds a day out, and that's what you've been getting for the last 2 weeks, I think that's still a good recovery for your money. So that's a decision that has to be made individually. And then with phytoremediation, planting your trees closer together, again, will reduce the amount of time required. So next I'm going to move into the decision tree principles, which are the founding parts of the decision tree. And like I said, once you grasp these, the decision tree is only sort of like something you can send to a consulting firm to help them understand it. There are basically 5 categories. Site characterization and DNAPL is a fairly quick principle. Then there's groundwater quality, time available, sensitive receptors, and geochemistry. Site characterization and DNAPL, some basic questions that the decision tree asks. And this is going to be on page 9 of the chlorinated solvent decision tree. And I wanted to say that I will give you the page numbers, but I had to break it down to make it into a presentation that you could actually read. So it's not going to be every page is not going to follow along the way that it is in the slide presentation. But I will give you the reference on the page that I'm talking about as we go through. So these questions are on page 9. Is the site adequately characterized? Obviously, if you are not confident in the delineation of the plume, Keisha says that's on page 7. See what's on page 9. Yes, thank you, Keisha. Page 7. Is the site adequately characterized? If there's holes in the plume, then the chlorinated solvent decision tree says let's go ahead and get it characterized first. But you can use the indicator parameters and the suggestions in the back for water quality monitoring to help you fill in those holes. And secondly, is contaminated fractured rock or DNAPL suspected or present at the site? If you have DNAPL or fractured rock, then you really need professional judgment to make good decisions. And the decision tree is really for unconsolidated materials without DNAPL. I think some of these technologies apply to DNAPL. You just have to be very careful how they're implemented. Groundwater quality is a big issue. If you're going to use the chlorinated solvent decision tree, then you're going to need to be sure that your groundwater samples are representative of the aquifer. And one of the big parameters that we use is oxidation reduction potential. If you measure that in an open container, open to the atmosphere with a probe stuck in it, you're not going to be getting an ORP representative of the aquifer. you're going to be getting an ORP that represents interaction of the water coming out of the well with the atmosphere. Bailers just do not work for measurement of ORP. I have seen some sites try to measure DO directly in a well without doing any purging, just lower a probe down the well. That doesn't work either. And I actually have an EPA document about that being unacceptable if any of you need that. So you really need a closed flow-through cell to prevent interference from the atmosphere if you're looking at ORP or DO. And as I said, for chlorinated solvents, bailing and no purge sampling should be avoided because you're not really getting representative samples. So this is a picture of a flow-through cell being used at the Thermalchem site. Don't know if y'all can see my little, can y'all, Robert, see the laser pointer? So this is actually the flow-through cell. The water's coming out of the well, going into the bottom. It goes through the cell. This is the multi-parameter meter that measures different, like DO, ORP, pH conductivity. So it measures it as it's flowing through the cell, and then it flows out and discharged into the container. So the chlorinated solvent decision tree is divided into categories based on groundwater quality. I came up with this division. You can use a different division if it suits your purposes. But for the sake of the decision tree, low concentrations are considered to be less than 50 times the remedial goal. So if you have PCE, your remedial goal is 5. If you have 100, then that's considered a low concentration according to this decision tree. Medium concentrations are between 50 and 1,000 times the remedial goal, and high concentrations are over 1,000 times the remedial goal. So the question comes up, how do you determine the plume concentration? Should you average? I've got 20 points, and some are above 50 and some are above 1,000, and what should I do if portions of the plume fall into different categories? And with that, I'd like to introduce our first case study. We'll be looking at this a couple of times. This is the colored map that you have with, as you can see up here. And this is a real site. I did not make up these numbers. I did not make up the colored contours. But I decided to call it the Midnight Dumping Site because if I gave the name of it, I might get in trouble. Directly adjacent to a surface water body, and the yellowish stuff is 10,000 parts per billion. And for the sake of argument, I'm going to say the MCL is 20. So what I did was just change that graph on the left-hand side to how many times the MCL. So the reddish, yellowish becomes 1,000 times the MCL, and then 50 times and less. And that's the first step. And then the second step is looking at high, medium, and low. You can actually divide that plume into different parts. And no, you don't average. You just do a spatial analysis of what makes sense to you. So this is going to be our initial treatment zones based on water quality, where the high concentrations are going to be active remedies or thermal remedies, which is the red area of that plume. The yellow is going to be active, and the green can be passive or active depending on your type of receptors. And with that, we're going to have another 5-minute break, but I will take any questions at this point. Yes, Keisha. The question is, will the PowerPoint be available? And I believe it will be posted as on e-learning. Is that correct, Marilyn? Yes. Pat, did you have a question? I'm sorry, David? Yes, we are. I asked them to turn it down as low as they possibly could. Now, the truth of the matter is I'm told that everything in the building depends on the temperature in this room being maintained at a certain temperature. That's the story, and they are sticking to it. Constantine? For soil mixing, how big of an area is appropriate? Soil mixing can be expensive, so it does, the smaller source areas are more cost effective to do soil mixing. We looked at a 100 by 100 area for soil mixing in Charleston, and I want to say the cost was a little bit over $100,000. If it's solid clay, so what you're doing, if it's solid clay and you're mixing in an amendment of some sort, then you're at least getting the amendment in there and you are creating more permeability within that clay. But I don't know that it's going to treat the clay completely. You know, you're still going to have contamination. Soil mixing is really ideal when you have stratified lithology, where you have some clay and some sand. Small lenses. So the question was, what do you do when you have all clay and you want to do soil mixing? Or not? Yes, Jim. Jim wants to know, are there VOCs in the stream? And that will be I will let you know about that. Stay tuned for the next case study. Okay, another 5-minute break, and I appreciate y'all coming back on time. Okay. Okay. I know Anthony didn't want to mess with it because the camera's not be able to show him. You know what I'm saying? Yeah. Right. The nice thing about 5-minute breaks, it is enough time to go to the bathroom and get back because the bathrooms are close. But that's about all you can do. You can't go back to your office and check email. Okay, so back to the decision tree principles. Let's talk about time available. How much time do you have? Time frames. Okay, so if you have contamination in that creek at that site, you're not going to want to do a technology that's going to take you 100 years if you have exposure going on. If you have nearby sensitive receptors, then you're going to want a faster time frame. I think everybody agrees with that. Does anybody disagree with that? Some companies, they're trying to redevelop their property. They want a fast time frame because they want to sell. I had one project, their goal was to be done in 5 years, and they had a massive plume. It was huge, and they pretty much accomplished their goal. 90% of that site has been redeveloped. That was up to them. I am never going to tell somebody no if they want to clean up quickly. There are options for faster time frame. There are the thermal remedies as well as some active remedies that you can over-design to speed up your time. So who determines what the time frame needs to be? Well, ideally, it's something we agree with the facility on. That's what we would like. If we're aware of sensitive receptors, then we're going to be asking for that to be done quickly, and hopefully they will not say no, but at least we tried. And that's our goal, is to get it cleaned up. So what is a sensitive receptor? I'm sure everyone in this room knows, but for the sake of the training, we have discharge of contaminated groundwater to surface water, which is one of the questions that Jim Bowman asked. What about that creek next to that site? Yes, that's a concern if there's contamination going there. And not only if it's ongoing, but if it's potential. If you think that creek is going to become contaminated at some point in the future, then it needs a higher priority to get cleaned up than something that is 10 miles from the nearest surface water body and there's nobody being affected. So if there's potential, if it's ongoing, it should affect the time frame that you choose for your site and the type of injectate that you're going to use. Of course, the other obvious thing is nearby water wells. Irrigation or drinking water, both can be of concern. If they're currently impacted, definitely high priority for getting something done quickly. I had a site, this decision tree is version 2. I saw how the first decision tree was used, and I realized that some things needed clarification. And one thing is, if you have a site and the drinking water wells have been closed and shut down because of contamination, that still qualifies for expedited time frame. We need to go ahead and get that taken care of, even if nobody's drinking it anymore, because they ruin those people's drinking water wells. And again, if there's a potential for these drinking water wells or irrigation wells to be affected, then you still need to consider a technology that's more active. Sometimes the type of injectate you're going to use needs to consider adjacent drinking water wells. Same with surface water. Sometimes you have to think about how that amendment will affect surface water quality. The other sensitive receptor is residences or commercial buildings. Vapor intrusion, that's sort of new on the radar screen for an old-timer like me, that we have to start thinking about, are people breathing it? Because if they are, we need to take care of it quickly. And again, need to consider the amendments that you're using, the technology you choose so that you don't make the vapor intrusion a worse problem. If receptors exist and site-related contamination is present in surface water, drinking water, irrigation wells, indoor air, we want to reduce time frame. We want to get it cleaned up quickly. That's one of the principles behind the chlorinated solvent decision tree. It prioritizes sensitive receptors. If they are threatened, as I said, we still want the reduced time frame. If they are abandoned because of the presence of contamination, we want a reduced time frame. So we're back to our case study, and the plume is intersecting the stream, and it's considered, the stream is a sensitive receptor. What is an appropriate response? What sort of time frame should you apply here? Obviously, this one needs a technology that's going to work quickly. I would even go so far as to say, go ahead and try to capture the contamination before it enters the creek with some type of recovery trench or recovery system. Innovative technologies are good, but sometimes you just have to stop the plume with containment technologies. So Jim, yes, there was contamination in the creek. Just really dismayed when I saw that. And finally, I want to get to probably the bulk of the decision tree that's complicated is the geochemistry part of the decision tree. So I came up with this must-have. I don't know if any of y'all ever looked at eHarmony, but you used to put a list of must-haves in your when you were searching for a relationship, that they must be blankety blank and do this and that and the other. So I thought, well, it's the same with geochemistry. There's some must-haves with the decision tree. And the must-have for the decision tree is your groundwater samples must be representative of the aquifer and the plume. And for this reason, the decision tree recommends low flow purging and sampling using a flow-through cell to measure indicator parameters once stability has been obtained. And the decision tree does not recommend bailing, no purge sampling, lowering probes into wells. That needs to be avoided. And that's another thing that came out of the first decision tree when we sat down and started trying to use it, and we realized the data quality is so terrible we can't use it. You know, we've got samples from bailers, they dried out the well, they had water trickling into the well, they grabbed a sample as soon as it was available. That means nothing. It's just, it's information, but it's not something that's usable. So that was a revision to this current decision tree. So as I said before, the decision tree wants to maximize remedy performance and optimize your cost by enhancing what's already present. If you have an oxidizing aquifer, the decision tree is going to recommend an oxidizing technology, and that's specifically with respect to active technologies. If you have a reducing aquifer, the decision tree is going to recommend a reducing technology. There are some showstoppers which came up as I reviewed the file. It was like, oh, this is going to make it so it doesn't work at all. So even if you have a reducing aquifer, there are some times that some of the reducing technologies will not work because they have certain components to them that cause a problem within the aquifer. And I tried to cover this in the decision tree. And again, for the sake of the decision tree, I divided oxidation reduction potential into 3 categories. Anything that is greater than plus 100 is considered an oxidizing aquifer. And for active remedies for an oxidizing aquifer, the decision tree is going to recommend either in situ chemical oxidation, air sparging, or ozone sparging. And this is, you'll find this in writing, I promise. Reducing conditions for active remedies. If your ORP is less than negative 100, then the decision tree is going to steer you towards a reducing remedy, which will include things like reductive dechlorination and zero-valent iron. Those are the 2 most common. And then we get to the neutral conditions between negative 100 and plus 100. So that's sort of in the middle, and I think you can pretty much do any technology you want as long as there's no showstoppers present for any of the technologies. And we'll get into that in more detail. I'm actually going to show you the components of the decision tree that pertain to this. But these are the principles. So you can pick up your water quality information and say, okay, I've got ORP neutral, I've got positive ORP, I've got a negative ORP, so I need a remedy that goes with that. So you don't even have to check the decision tree for that. So there are some showstoppers. I'm having a hard time saying that. pH can be very important with respect to reductive dechlorination or chemical oxidation. If your pH is too high or too low, it can cause fouling, or it can cause the technology not to work at all. Sulfate is important when you're looking at zero-valent iron, and nitrate has a pretty big effect on reductive dechlorination. Sometimes we have found petroleum products in the subsurface actually assist reductive dechlorination. We have some dry cleaning sites next to gas stations that have cleaned up amazingly well. And it's primarily because of the petroleum and co-metabolism that happens when the petroleum is present and the bugs are there eating the PCE. It stimulates those bugs. And it actually gets down to ethene without having to go through the process that we normally are associated with. I'll take questions at the end. So back to our little case study. So we've got an oxidizing aquifer with the ORP between plus 75 and plus 350. The typical ORP of the site is around plus 200. So in this case, an oxidizing technology should be considered. But if you do look at in-situ chemical oxidation for the site, then you're going to have to look at what's going to work for that stream, adjacent to the stream. You would not want a technology like permanganate that's going to give you purple water in the creek. You would want to pick an amendment. If you were going to go with ISCO, you want to pick an amendment like Fenton's reagent that has like a 24-hour lifespan. Or you would pick some other type of technology like air sparging or even groundwater recovery to prevent contamination from getting into the creek. And we're at the point where I can take questions, and I think Marilyn has got a microphone that we're going to try to use so that I don't have to repeat the question. Well, since Anthony is recording this, hello, Anthony. We love you. We thank you. We appreciate you. Marilyn Tim has a question over here. He'll cut that out of the recording, I'm sure. Except maybe to show his wife.
What is the interaction between sulfate and zero-valent iron that you had in that previous slide?
So sulfate is going to corrode zero-valent iron pretty rapidly, which is going to make it use up all of its bang very quickly. Now you can add some additives to reduce the corrosivity of the sulfate, but it's something that needs to be considered as part of the design. Jan?
So what would your sulfate numbers be?
So in the decision tree, when we get there, you'll actually have numbers that you'll be able to look at. I'm just giving you the principles now, and then you'll see actually how it all gets put together. Anybody else? Okay, I'm sorry, but it's another 5 minutes. 2:02. She put it in the microwave for me. Thank you, Angie. One-minute warning. I'm getting used to it. It helps. You're going to send me a picture of y'all in your shorts in January. I know it. Okay, it's 2:07, so I'm going to go ahead and start back. We're actually going to get into the decision tree now that we've talked about the principles behind the decision tree and the research that went into it. And we're going to talk about the individual components. I have to say up front that, and give this disclaimer, this is not a regulation. I would love for it to be a regulation, but it's not ever going to be a regulation. It's for informational purposes. It can be shared with consulting firms. We actually went through a public comment period back in 2011. This information was presented, and we did some modifications based on some of the public comments. So it can be sent out if you would like to individuals that you feel like would be benefited by it. But it's not a requirement, and you don't ever have to use it if you don't want to. So I'm going to first start talking about innovative technologies for groundwater remediation. The decision tree also has a part on pilot studies and monitoring recommendations. For innovative technologies for groundwater remediation, the decision tree is divided into thermal, active, and passive technologies. For thermal technologies, we have some key questions. Are concentrations over 1,000 times to 50 times the remedial goal? Or is a reduced time frame desired? So obviously, if you're over 1,000, thermal is appropriate. If you're between 50 and 1,000, well, if you're in a hurry and you want to, it's probably okay. I don't think anybody's going to propose thermal for something that's 10 times the MCL. Just don't think that's going to happen. It's not cost effective. But anyway, those are the key questions for thermal technologies to start with. And part of this is on page 8 of the decision tree. And as I said, it's not going to look exactly like you're seeing it in the decision tree because I'm trying to make it understandable in this presentation, and I can't fit everything on one slide that's on one 8.5 by 11 piece of paper. So I broke it into pieces. So this shows the questions that I just mentioned. Are constituent concentrations greater than 1,000 times the MCL? If yes, is a reduced remediation time frame desired or needed? Yes. Then thermal technologies, the decision tree is going to direct you to a thermal technology. Some more questions pertaining to thermal. There are actually different types of thermal technologies. So some of them are better depending on whether you have recharge of groundwater or not. Some of them do better if the water table dries out, and some don't. So the questions in the decision tree: is the water table shallow? Is recharge to groundwater minimal? Are groundwater flow rates low to moderate? And if all of these are true, then thermal wells are going to be recommended, because thermal wells like to dry out the ground. And it's really wonderful if you think about drying out clays and heating them up, you can really drive off a lot of contamination out of those clays. But thermal wells are not effective if you have a lot of groundwater coming in that changes the temperature of the subsurface. So you want low recharge in this case. And you're going to find this on page 14. So, as I said, in the upper right-hand corner, is the water table shallow or is recharge to groundwater minimal? Yes. Are groundwater flow rates low to moderate? Yes. Then it's going to lead you to thermal wells in the bottom left-hand corner. However, if your water table is not shallow or if recharge to groundwater is not minimal, if you have a lot of water in the vadose zone, then the decision tree is going to recommend electrical resistance heating. That's because electrical resistance heating depends on moisture being present, whereas thermal wells do better when moisture is absent. So that's just a little bit of information for you on thermal that I learned by looking at how these different thermal technologies actually worked. So we're going to move from thermal to active technologies and go over some of the key questions for active technologies. If your concentrations are over 1,000 times a goal and you do not want a reduced time frame, you're not in a hurry, then active technologies can apply. If the concentrations are less than 50 times your goal, but you want to clean it up quickly, active technologies can be considered. And I believe this is on page 8, I hope. Are contaminant concentrations above 1,000 times the NCL? No. Are they between 50 and 1,000 times the NCL? If you go straight down the middle, it takes you to yes, and that takes you to other active remedies. If the constituent concentrations are not between 50 and 1,000 and they're not over 1,000, do you want a reduced time frame? If yes, then we're going to other active remedies. Now that we're into active remedies, so we're moving through the decision tree, the next question is ORP greater than 100 millivolts? If yes, consider oxidation technologies. Is ORP less than negative 100? If yes, the decision tree is going to recommend reducing technologies. And then again, if you're between those plus 100 and minus 100, the decision tree is going to have a section for neutral ORP technologies. You're going to see part of this on page 9 for other active remedies. And again, it shows is the progression of the questions. Is ORP greater than plus 100? Yes, then it takes you to active oxidation remedies on the upper right. No, then it takes you to the next question, is ORP less than negative 100 millivolts? Yes, then you're going to active reducing remedies, and no, active remedies for neutral ORP. I hope you understand why I wanted to go over the principles first, because this progression is a little complicated if you don't get the principles. So we're moving into active technologies with chemical oxidation. And to select a chemical oxidation technology, the key question really is there an existing or potential impact to a well, surface water, or other sensitive receptor? If you do have something that will be affected by injection of an oxidant, it's important to think about the amendment type and the response action. And the decision tree is going to recommend something like ozone sparging, air sparging, or amendments with a very short lifespan. If you don't have sensitive receptors, then there's a lot of choices for the amendments that you can use for chemical oxidation. This should be on page 10. It shows the same questions I just talked about. It's just in a diagram. ORP greater than 100, yes. Is contaminated groundwater currently discharging to surface water? No. Are there impacted public or private wells with irrigation or irrigation wells? No. Is there a potential for contaminated groundwater to enter surface water, a private or public well, or an irrigation well? No. In that case, you can look at any amendment, as I said, and that's what the decision tree is going to show you. Ozone, permanganate, Fenton's, persulfate, any other oxidant type amendment would be acceptable. But then we have chemical oxidation when you have nearby receptors, nearby sensitive receptors that we need to look at, and the decision tree includes this. Should be on page 10. Is contaminated groundwater currently discharging to surface water? Yes. Are there impacted public or private wells or irrigation wells? Yes. Then the decision tree is going to point you to ozone sparging or air sparging. It's not going to point you to any type of injection of amendment. And there's a little note in here that soil vapor extraction may be needed in conjunction with these technologies. Sometimes if you implement these technologies and you don't have soil vapor extraction, you just spread the contamination around into the vadose zone, and that's not really desirable either. So finally, we're back to the potential. So not only is it currently occurring, but is there a potential for it to occur? And this is a judgment call on your part based on your understanding of the site conditions. If you think there's a potential, you still need to be conservative in your choice of amendment type. And the decision tree does recommend bench scale and pilot testing to confirm the longevity of the amendment in the subsurface. So I would go somewhere at a distance from a private well if I was going to try a particular amendment to confirm, yes, this is only going to last 3 months. Or because sometimes the amendments will last longer in the subsurface than you expect. We have at least one dry cleaning site where they put in permanganate and it's still there 3 years later. So it's important to know. Okay, believe it or not, we're at the time for questions and another short break. So does anybody have any questions about active technologies, chemical oxidation? Constantine, microphone is coming.
About definition of active technology, why is thermal not an active technology?
Well, it is. It is. It's just an active one that's extremely, I guess I could have called it extreme active technology. I just separated it out. The writer's prerogative.
When you were looking at all the different sites, did you find anywhere the ORP varied enough that you would actually kind of be having a couple decision trees going on at one particular site?
Yes. In fact, I'm going to be presenting one case study from a site that had strongly positive ORP near the source area and strongly negative ORP adjacent to surface water. And so in those cases, you do sort of like we did with the water quality, where we divided the plume into different treatment zones. And we actually used both an oxidizing and a reducing technology at that site. And they are running around broadcasting victory. And so I'll be glad to give you the name of that site later.
And then, I guess, as a follow-up, so then when you're doing this, I would assume that your ORP can change as you're implementing these technologies, so that you have to make sure you have monitoring, because then
What's coming into your system?
Right.
Well, once you've got a technology implemented, there's not a whole lot you can do about it. I mean, it sort of depends on the longevity of the technology, and if you're doing ongoing injections, yeah, you might take that into consideration, but if it's a one-time injection and you see changes, you know, it's not a whole lot that can be done about it. Okay. I will see y'all at 2:25. Gives you a chance to go outside and warm up for 5 minutes. Everybody's leaving. Is it just going to be you, Joe? Boy, they sat through the last frame of this one, though.
They were waiting to get to the decision tree itself.
Only if it gets suspended in air. I could think of dust. PAHs and dust could be an issue. I would think dust monitoring. Don't want to breathe it in. You don't want to breathe in PAHs. That's why people aren't supposed to smoke cigarettes. Smoke PAHs. I'm not talking to you, Jan. Okay, I want to go ahead and get started because I do want us to finish. I do think we will finish early. As I was going through these slides, I noticed that there was some duplication, and y'all have probably picked up on some of it. Some duplication's okay, but I took out some of the duplicates, so I think we'll be done before 4 o'clock. Okay, we'll start back with active technologies reducing remedies. And I refer you back to page 9. And this slide shows the question, is ORP greater than plus 100 millivolts? No. Is ORP less than negative 100 millivolts? Yes. Then the decision tree is going to send you to active reducing remedies. There are some key components to reducing remedy, and this is one that some people find controversial. My research has shown that the pH needs to be 6 or above for in situ bioremediation and reductive dechlorination to work. If the pH is greater than 6, all reducing technologies may be considered. If pH is less than 6, the decision tree is going to recommend zero-valent iron, but pilot testing is also something that the decision tree will recommend if the responsible party is insisting on a bioremediation type of remediation. Secondly, does groundwater contain nitrate? If there is nitrate in groundwater, then that's going to be a problem for reductive dechlorination. I actually have a paper that is referenced in the decision tree that you can use and cite at your projects if you have a proposal for reductive dechlorination and they have nitrate in groundwater. I actually have a good reference in the decision tree about that. So with nitrate, zero-valent iron or air sparging is recommended. If there's not nitrate, then reductive dechlorination or zero-valent iron are considered viable. This is on page 12, I believe, of your decision tree. Starting on the right-hand side, which drives engineers crazy, is pH 6 or higher? Move to the left, yes. Does water contain sulfate or nitrate? No. Then ZVI and ERD are considered viable. I believe you'll find this on page 13 in the decision tree. Is nitrate greater than 1 milligram per liter? That's the number Jan was looking for, I think, or I think you're looking for sulfate, but this is a nitrate number. Yes. Be very cautious before applying reductive dechlorination. The research has shown that dihalococoides cannot survive in the presence of this level of nitrate. Zero-valent iron may be feasible, and air sparging would be feasible. If nitrate is not over 1 milligram per liter, then you can look at zero-valent iron and enhanced reductive dechlorination. Now we move to the questions about sulfate and petroleum. Does groundwater contain significant amounts of sulfate? If yes, fouling may be an issue for zero-valent iron. Does groundwater contain petroleum products? This can stimulate biodegradation of chlorinated solvents, even if the pH is below 6 through a different process than the one that we're used to. It's called co-metabolism. But a pilot study would be needed to confirm that you can actually achieve your remedial goals with that. So here it is sulfate greater than 20 milligrams per liter? There's a couple of references on that. Yes, reductive dechlorination may be considered, but you need to look at longevity estimates for zero-valent iron, and there are some amendments that can help with the corrosivity issue for zero-valent iron. If the sulfate is not over 20, then both zero-valent iron and reductive dechlorination can be considered. And I believe this is page 13. Back to page 12, looking at pH is pH 6 or higher? No. Are petroleum products present? No. Then the decision tree recommends zero valent iron. If the facility insists on reductive dechlorination, then a pilot study would be in order. This is just a recommendation from the decision tree. So if they want to prove that they can get it to work, if they want to do some type of bioaugmentation, then they can do that. This just needs to be demonstrated before it's selected as a final technology. And I believe this is on page 12 as well. Is pH 6 or higher? No. Are petroleum products present? Yes. A pilot study may be needed prior to selection of reductive dechlorination. Moving to ORP neutral technologies. Key questions. Is pH less than 6? Sorry, you're going to hear it from me 2 or 3 times. South Carolina, the groundwater in most parts of South Carolina can be less than 6 naturally without any contamination being added. That's why so many reductive dechlorination remedies do not seem to be successful, because Dihalococordias does not do well if the pH is less than 6. No matter what you do to it, no matter what sort of carbon source you give it, it's just not happy. And there is documentation about that. I had one site where the pH changed and all of a sudden reductive dechlorination went off the charts and everything went down to 0. But that was after the pH went up, and I can't tell you why it went up. It went up from like 5.8 to 6.2, and all of a sudden, boom, everything happened. That was my first clue to look into that a little more. For ORP neutral technologies, another question, are significant concentrations of sulfate or nitrate present in groundwater? If the answer to either of these conditions is yes, the decision tree is going to send you to an oxidation technology. Otherwise, a reducing technology can be considered. I believe this is on page 16. Active remedies for neutral ORP between negative 100 millivolts and plus 100 millivolts. First question, is sulfate greater than 20 or nitrate greater than 1? If yes, then it sends you to active oxidation remedies. If no, then the decision tree asks, is pH 6 or higher? If yes, it sends you to active reducing remedies. If no, most technologies are viable, but again, you want to look at some type of a pilot study for reductive dechlorination. Am I going too fast? Does that sort of all make sense? Okay, passive technologies, key questions. So this is when we're less than 50 times the remedial goal. Are contaminant concentrations less than 50 times the remedial goal? If yes, a passive technology may be considered. Is a reduced remediation time frame desired? If you're not in a hurry and there's no receptors, then perhaps a passive technology can be considered. But if there are sensitive receptors, such as a surface water body or drinking water wells, or even vapor intrusion issues, the decision tree is not going to recommend a passive technology. So here's what that looks like on the decision tree itself. Are contaminant concentrations greater than 1,000? No. Are they between 50 and 1,000? No. So that leads you to passive. It leads you to the assumption it's less than 50. And this is on both page 8 and 15, I believe. Is a reduced time frame to meet goals needed or desired? Yes. Then it's going to send you back to active remedies. No. Then the question becomes sensitive receptors. Are nearby wells or surface water bodies impacted by contaminants? Has a well been abandoned because of impact? Are residents or commercial buildings located anywhere in the area where vapor intrusion could be of concern? Is there a potential for these things to occur in the future? And during the break, I had a question about, well, how far away does the sensitive receptor need to be before it's no longer of concern? And that really depends on your hydraulic properties. If the aquifer is moving groundwater at 1,000 feet per year, then your sensitive receptor that's 50 feet away is going to be a big problem. If your groundwater is moving at 10 feet a year and your sensitive receptor is 100 feet away, then maybe not. So it's a judgment call that you have to make based on your understanding of how fast groundwater is going and how close the sensitive receptor is to the area of contamination. So some key questions for passive technologies. Is the water table shallow? If not, the decision tree is going to recommend monitored natural attenuation. We're basically picking between M&A and phytoremediation at this point. There are some phytoremediation people that claim they can make these trees' roots go really deep, and that is a technology that can be pilot tested and demonstrated if they want to do so. But the decision tree picks the simple route and says M&A if the groundwater table is deep, and phytoremediation or M&A if the water table is shallow. And I believe you'll find this on page 15. In this big square on the left, again, is a sensitive receptor question. You got wells, you got stream, you got people breathing potential contaminated air. No. Is the water table shallow? Yes or no? If it is, phytoremediation or M&A. If not, then go ahead and consider M&A. Okay, so these are like 10-minute sections. Does anybody have a question at this point for reducing technologies? And I did have a question about what contaminant do you use to decide if it's 50 times or 100 times or 1,000 times or less than 50. And that's your call. You can pick the most contaminated one, or you can pick the most toxic one. It's your call on which one you want to drive the decision tree. So questions coming, the microphone is coming.
So what were the numbers that you would find in the naturally occurring in the groundwater with the pH in South Carolina?
I'm
What
sorry,
kind of numbers would you see that are
naturally occurring? We have a site in Kershaw County where the naturally occurring pH is 3. That's the worst I have seen. But typically I see 5, 4.5. Anybody else see? I mean, every now and then you find a site with 6 or 6.5, and that's really nice. If you get towards the coastal plain, towards the coast, and we've got a little bit of lime mixed in there, you can actually have a pH over 6. But I would say 3/4 of South Carolina is going to be below 6. And there are companies that proclaim that they can change the pH of an aquifer. And we have seen that fail miserably because pH is a normal scale, a logarithmic scale. It is not an arithmetic number. So you can't just add twice as much calcium carbonate as water and expect the pH to double. It doesn't work like that. And again, you have the fouling issue when you start trying to change pH. And that was actually demonstrated at the same site that has the 2 technologies in place that we'll be looking at, where they tried to change the pH because they wanted to do bio across the entire site. And I told them they needed to demonstrate they could change the pH. And it failed. Absolutely failed. Other questions? Jim, Marilyn's coming to you.
Judy, you realize this is about chlorinated solvents, but do any of these principles generally could apply to metals, natural attenuation? Are there some deal killers that would prohibit even consideration of metals, natural attenuation? Well,
certainly with something like, I'm just thinking of zero-valent iron, you can actually use that to treat some metals in groundwater. So I think the issue would be whether the stuff in the groundwater would eat up that ZVI pretty fast. And so I'm not sure if that answers your question or not. Did I get your question right?
It does. If someone was proposing ZVI for metals, you could still consider some of the parameters.
Well, certainly if the groundwater's oxidizing and they have metals. You know, trying to address the oxidation state of a metal is one way that they do remediation. Sometimes ZVI works, but you know, I'm having a hard time right now coming up with an oxidizing technology that would treat metals. So I'm not sure it entirely works. There are some of the principles could be applied, but I'm not sure it would be applied across the scale, across the board. I think of chromium, you know, that's the one that I think of the most when you talk about metals. And for chromium, we have zero valent iron and we have molasses. Those are both reducing technologies. I don't know of an oxidizing technology that works for chromium because you're trying to change the state from oxidizing to reducing so that it will become immobile. So I think it's slightly different.
I've got one site where a reducing technology is proposed for the metals remediation, but the pH is so dang low that they're saying can't be done. pH is too low; it'll just consume whatever
Right.
high pH injectant you put into it.
And that's when it comes down to those basic chemistry equations, and I'm so much in favor of. If you understand the basic chemical structure, you know, the process, the reactions, then you'll be able to give a good guess as to whether it's going to work or not. And that would make sense to me. That yeah, the pH could be too low for those technologies.
Okay. Can I keep this?
Anybody else? Okay, 5 more minutes. I think we have 1 or 2 more presentations left. thinking nobody's going to come back. All right, they've got the information they need. No. Okay, we're already at 2:49 p.m. So the bulk of the core of the decision tree, we have talked about how things go with chemistry and receptors and stuff like that. That's really the key part of the decision tree. But I also, while I was writing it, decided that we needed a little bit more information on pilot studies that we could possibly share with consulting firms. Because the decision tree recommends pilot studies in certain cases, I went ahead and put together some guidelines for pilot studies. So we'll talk about purpose and benefits, technologies that can be pilot tested, pilot studies performance evaluation for injections, key components of successful pilot studies, and technology-specific issues. There's even some technology issues that could go along with pilot studies. So if you have a good pilot study, if it's properly designed and executed, then you'll know whether or not your technology is going to be suitable for your subsurface conditions in the area of concern. Pilot studies are going to help you figure out what site-specific factors affect that technology and its performance. And as you saw when I was talking about the components of the decision tree, pilot studies are recommended if there is an injection technology, if geochemistry of the technology may not be compatible with the subsurface geochemistry. It's really a good thing to do a small-scale pilot study to see if that's really true or not. So here are some of the purposes and benefits. To confirm the design criteria for your injection technologies. How much can you get in the ground? How far is it going to go? Are you going to have a 150-foot radius of influence as the consulting firm proclaims, or is it more like 10 feet or 30 feet? Sometimes you don't really know these things. Are you going to have daylighting? Is it going to just clog up the minute it goes in the ground and start coming out the hole where the injection is actually occurring? All of this is going to help you know how much it's going to cost, which, you know, in theory, we don't really get so caught up in cost, but it's good to know when we're doing like a feasibility study and they say, well, this technology is going to cost us $55 million. And we're like, wait a minute, you did a pilot study and your radius of influence is big enough, you probably only going to spend $10 million on it. So that helps us too. So it will help you define the effectiveness of the technology as well as longevity, especially if we're talking about some of these oxidants and we're looking at sensitive receptors. We need to know, is it going to last a day, a week, a year, 3 years? That's going to tell us how far away from that receptor we need to go. So there are some detailed guidelines in the back of the decision tree pertaining to pilot studies. Talks about the types of objectives that are needed for pilot studies and also discusses issues pertaining to pilot studies for particular technologies. And here's a pilot who's not in the room at this time. I think he's flying a plane somewhere else right now, back there in the back. So you can easily test reductive dechlorination and in situ chemical oxidation. We have done a pilot test of a permeable reactive barrier. It's not necessarily the cheapest way to go, but sometimes that's what you need to do. You can easily pilot test chemical reduction or zero valent iron. You can pilot test air sparging if you want to. Less amenable technologies, phytoremediation. It takes forever to establish a tree system to see if you're going to be able to phytoremediate something. Why would you pilot test the thermal technology? If it costs you $1 million to build the thermal system, then you might as well do full scale. And we have, really with thermal, it's more of how long does it need to operate rather than can it work. As long as it's designed properly, it should work. And again, permeable reactive barriers can be pretty expensive to pilot test. So here are some of the performance questions that can come out of an injection pilot study. How much injectate is going to be required to achieve your desired results? How many treatment events are you probably going to need to achieve those goals? Do you create any byproducts that are more toxic? For instance, do you stall out at vinyl chloride? And you can't get past vinyl chloride, and all of a sudden you have all this vinyl chloride accumulating. I think that's a good thing to know before you do that on a full scale, that we can't get rid of our vinyl chloride. We need to look at another technology. For zero-valent iron, sometimes you need to have enough of it, or you will also create vinyl chloride. If you just have too little zero-valent iron, it can be a problem. Do you have mounding? Most of the time you will with injection technologies, and for that reason, sometimes outside-in injection is recommended, where you start on the outside of the plume. So if you mound, you're pushing things, clean water away and dirty water in. So you start out and work towards the core of the plume. There was, I believe it was an air spurging technology that actually caused a clay layer to collapse, and the groundwater suddenly declined like 10 feet in the wells that they were monitoring. That was interesting. You can also look for dilution. If you look at some of the basic indicator parameters, you can use them to say, well, we didn't change the ORP with this oxidation technology, but gee, our concentrations went way down. Guess what? You probably just diluted. You injected so much, you created dilution, and that's why your numbers look so good. Pilot studies can also give you some idea about rebound and back diffusion, especially rebound. Back diffusion takes a while to evaluate, but you can get that information out of a properly designed pilot study. Co-solvency. We were just talking during the break about emulsified vegetable oil, and there's actually a site not in South Carolina where they injected vegetable oil, and all of a sudden their groundwater concentrations went up into the tens of parts per million range when they were less than a part per million to begin with. And it turns out the vegetable oil actually extracted the solvent from the subsurface. And then they were smart enough to recover the vegetable oil, and they did a great job cleaning up that site. But that's something that's helpful to know during a pilot study. So here's some performance evaluation questions. How much injectate is the ground able to receive? What's the radius of influence? How long is the amendment actually going to last on the shelf? How long is the amendment going to last in the subsurface? They have some idea of this for the companies that implement these technologies all the time, but subsurface conditions vary from site to site. The pilot study is going to help you with that. Biofouling and fouling. I think that is one of the best reasons to do a pilot study. If there's a potential for biofouling or fouling, so much better to find it out up front. Are there permeability limitations and effects? Are you going to have trouble injecting because there's too much clay? It's good to find that out before you select that as your final remedy for a site. Health and safety of the technology. Sometimes you discover safety issues in the field. One of my sites, they were doing chemical oxidation technology next to a wastewater treatment plant, and they forgot to vent the aquifer, and it was an exothermic reaction, so the foundation cracked of the wastewater treatment plant building. That was a good thing to learn. Equipment limitations. Sometimes there's just so much you can do with the subsurface based on the type of equipment that you have. Maybe you need a bigger rig. Maybe you need a different tool. Pilot studies help you know that. So, key components of successful pilot studies, they are so important. The location of the pilot study is very important, and I have recently looked at a site where they propose the entire plume for a pilot study. I'm not sure I would call that a pilot study. It's important to locate it where you have contamination, but you don't have more contamination coming in that's going to confound your interpretation of the data. Of course, you have to think about sensitive receptors again. You want to go where you have typical geology, typical contaminant concentrations. As I said, you don't want significant upgradient contamination that will confound your pilot study, and sufficient existing well coverage is helpful. The size of the area, large enough to be meaningful, small enough to be cost effective. You want to try to get your results in a year or less. If you have a 5-year pilot study, that's too long. It's just me. You might not be around. Nobody might be around in 5 years to see what the results are. The length of study is needed to allow evaluation of rebound after a technology has been implemented and you're looking for rebound. You might need to wait 3 to 6 months. If you're looking for daughter products, especially with reductive dechlorination, and you're looking to see can we get past vinyl chloride to ethene, maybe 6 to 12 months, might even be longer. Radius of influence, you can figure that out in 1 to 3 months. In amendment longevity, days to months. So this is the permeable reactive barrier that we did a pilot study on. And one thing that I learned about PRBs as I was reviewing how they performed in South Carolina is you put them in and they actually can affect the groundwater flow direction after you put them in. So what we do now is we try to make them in the shape of a V so that if they do change groundwater flow direction, the groundwater is not going to go around the end of them. But this is a great example of how it affected the groundwater flow direction. Is the pilot study area typical with regards to the hydrogeology? Do you know the groundwater flow direction? Do you have appropriate well spacing? And you can see we had a lot of wells. It doesn't have a scale there showing, but this was a very short permeable reactive barrier pilot test. The PRB was probably not more than 50 feet across, and we had, how many is that, like 18 monitoring points within that permeable reactive barrier and several around. Baseline sampling must be done if you're going to make comparison of your results to say the technology worked. Let's start by taking baseline indicator parameters like dissolved oxygen, ORP, pH, as well as contaminant concentrations. Depending on the type of technology you're looking at, you will be comparing those to what happens after the technology is implemented. Frequency of sampling is so important, whether it's full scale or pilot study. Don't wait too long to get data, and don't wait too long to look at the data. And of course, your analytical parameters need to be your constituents of concern, your indicator parameters, byproducts, process-related parameters, and showstoppers like the nitrate and sulfate that I was talking about before, pH. And of course, samples need to be representative of the aquifer. Okay, does anybody have any questions on this section? I think we'll forego the break. We'll take questions, and with your permission, we'll forego the break and move into the next subject matter. So, questions? Okay. There are some specific issues associated with pilot testing of certain technologies. With reductive dechlorination, as you may have guessed, if your pH is going to be less than 6, it may take an extended amount of time to determine if you're going to stall out at DCE or vinyl chloride. It takes some time to figure that out. It's normal to create DCE at the beginning. It's just how long are you going to wait until you see whether you get ethene or not and how much ethene you're getting. For reductive dechlorination, there's a number of different methods. You can enumerate microbial populations so that you can know is what we need there in the ground. If they need bioaugmentation, this is a good time to find out by just doing some relatively inexpensive tests for microbes, especially if the pH is less than 6, and if there is nitrate and they're insisting on pursuing this technology, then microbial enumeration would be helpful. And again, you want to look at your amendment longevity in the subsurface. If you're using molasses versus oil, your molasses is going to be eaten up pretty quickly. Your oil is going to last forever and gum up everything in its vicinity. And the desorption and co-solvency are, again, two things that happen when you're looking at reductive dechlorination that can be looked at during the pilot test, which is a lot better than looking at it full scale. Some of the things you can look at when you pilot test reductive dechlorination are the formation of volatile fatty acids. That tells you that the technology is actually creating those conditions that you want for reductive dechlorination to work. You can look at the daughter products like vinyl chloride and ethene. You can also look at the ratio of the parent to the daughter product to tell you, are you actually seeing that transformation? You can look at concentration trends. That's pretty basic. In situ chemical oxidation. This is ex situ chemical oxidation here. But in situ, venting is one of those things that I think needs to be considered, especially if you're looking at Fenton's reagent. Rebound is an issue associated with ISCO, and that's something that you can look at during your pilot testing. Something else that's important is the presence of utilities, underground lines, because if you do an injection of an oxidant, you can burn up your utility lines. You can also have preferential flow. This works for any type of injectate. If your underground lines have higher permeability, it can all go there and not go where you want it to go. And the amendment longevity in the subsurface is a question for ISCO. We have general ideas about how things last, but it's going to be a site-specific determination. So let's look at our case study that we have, the blue and yellow midnight dumping site next to the creek. And since we have a positive 100 plus 100 ORP, then we're going to look at a chemical oxidation technology. Where on that map would you recommend a pilot study? Unfortunately, I don't have a blank slide without the answer at this point. So you'll have to look at it for 1 minute. Yes. So where would you recommend it? Right in the core? I mean, that is certainly one option. If you do put it in the core, then there's a risk, if groundwater flow is towards the surface water body, that you will have contamination coming into it. And that's going to make it difficult to interpret the pilot study, because if your concentrations go up because of migration of contamination, that could counterbalance the effect of the pilot study. So I didn't put in a slide without it. But there's no magic answer to this. I mean, there are pluses and minuses, because if you put it in the core, then you're going to know, will it work on the worst concentrations? But I just moved it up a little bit, sort of towards the edge of the plume, with the assumption that groundwater is flowing towards the surface water. I just put it a little further out of the core to get a little bit of that core in there. And the concentrations flowing in there hopefully are a little bit less, so it maybe would not make the study as difficult to interpret. So monitoring recommendations. I've got several of them. First of all, adequate monitoring well network. If you do a pilot study and you have 3 monitoring points, I'm sorry, but that's a waste of your time and their money. Water levels, especially if you're doing injection technologies, but even with other ones, water levels are going to tell you something. And thirdly, water quality. So here is our next little exercise. It's sort of tricky, but you can look at your map and tell me, do you believe the monitoring well network is adequate? You want to have wells near the source area, near the plume boundary, adjacent to treatment areas, and even outside the plume to see if the plume migrates, which is called sentinel wells. Does anybody see anything about this map that may not be adequately monitored? Who notices? I see Sarah. Ken is waving his hand. Ken, what is wrong with this map? This is a real site. This is another NPL site, my NPL buddies. I'm not really smashing your program, but I have so many fine examples. Yes, Ken. There is only one limestone well. It has a pretty good network for the shallow aquifer, and it has a pretty good number of extraction wells and piezometers. But there's only one yellow dot towards the bottom. And I'm afraid that's not quite enough for me. Now, we argued with these people. I was involved with this site back when I was very young, trying to convince them they needed to put in a limestone well. This Kalama site, for you two that are working on it now. We argued for years that they needed to go beneath. They claimed they had a confining unit. They claimed, and we argued for a while, and they finally put that well in, and sure enough, it had contamination in it. And we continued to ask them for more. I don't know if they ever did put in any more, but this is what we had at the time. I hope they do put in more. Yes, there is an off-site well that's affected. Off-site limestone well. Okay, some notes on monitoring well network. Do not, please, allow a company to use injection wells as effective monitoring points. So you go out there, you inject an oxidant into the well, and the next day you take a sample and say, wow, it's all gone. Unless you let that well return to baseline conditions. If you know you're injecting an oxidant into a neutral setting where your groundwater ORP is 100 and you're injecting something that's like 500, you get 500 out of the well with your injectate. Wait till you get back down to 100 before you sample that well if you have to use that monitoring point. Extraction wells are not appropriate for water levels because there's well losses within the well casing. And you'll find some people do water level maps with extraction well data points included. That's not appropriate. You can optimize monitoring well network using direct push technology. It's kind of hard to go back to the same point again and again. So long-term data evaluation is better if you can actually have permanent wells, but you can use direct push to supplement that. Water levels are going to help you determine groundwater flow direction and changes based on seasonality. I don't know if any of you have sites where in different seasons the groundwater goes in different directions, but that becomes important when you're looking at a pilot test or even long-term monitoring. You also use those water levels to monitor for mounding during injection. So if the groundwater direction changes, then your remediation system has to take that into account to cover all the potential directions that plume could be going. And then again, back to my representative sample soapbox. Please use techniques that get you representative samples for water quality. Indicator parameters, constituents of concern, remedy byproducts, daughter products, and other. So this is another handout that you have that is part of the decision tree, which is indicator parameters that are recommended for different technologies. And I have highlighted the ones that really need a closed flow-through meter, the DO and ORP. The pH you can do pretty much in the atmosphere as long as you do it quickly. Total organic carbon really has to be done in the laboratory, but it does tell you if you are meeting some of your objectives. With ERD, you're trying to increase the total organic carbon. With ISCO, you're trying to eliminate total organic carbon. It will dissolve it if it gets there, if it contacts it. So that's for your use. And then we have, for reductive dechlorination, you can look at those volatile fatty acids. Dissolved metals are important to look at when you're injecting something to create reducing conditions, because you can actually release metals from the subsurface if you inject something that creates reducing conditions. There's some metals that say, oh, it's reducing, I'm going to travel, I'm going to go into the groundwater. And then we have also the sulfate and the nitrate, which are the showstoppers, and microbial enumeration. There's a couple of tests now. I like the quantitative polymerase chain reaction test, QPCR is the abbreviation. You'll see that in a lot of places. There's other companies that do something called biotraps, that they set it in the water and they look and see how many bugs come into those biotraps. The advantage of those tests is you can actually find out if you're missing like the vinyl chloride reductase. So you've got the halicocoides, great, wonderful, but you have the kind that's missing the vinyl chloride reductase gene, in which case you're just going to accumulate vinyl chloride. And at the Clemson Hydrogeology Symposium 3 or 4 years ago, there was a presentation that 25% of the sites in South Carolina are lacking the vinyl chloride reductase gene that they looked at. So that's something that's good to know. In situ chemical oxidation can also release dissolved metals. It's a different group, but it's definitely something to consider, good to look at during pilot studies. And then looking at the sulfate and alkalinity. Alkalinity can certainly affect the effectiveness of chemical oxidation by fouling. And chemical reduction, which is really zero valent iron for the purpose of this presentation, dissolved metals, sulfate, nitrate, alkalinity. Okay, we are at a break time. We have a practical exercise that we will end up with. Does anybody have any questions now that I have zoomed through the monitoring portion of the decision tree? And Marilyn is coming with her microphone. Okay, we will meet back at 3:20 and it will be the last section of the presentation. $11 more slides to go. Huh?
What is that method?
Methanogenesis. That is when they add too much amendment to the subsurface, it creates that methanogenesis, which slows down or shuts down bioremediation effectiveness. But it's not something that I put in this decision tree because the research really isn't there to say how bad it has to be before it is a problem. Deep soil mixing. You know where your source area is. time was it? I mean, what time did I say? Did I say? What did I say? 3:21? Okay. I can't remember what time I stopped. It seemed like it was 2:27, 3:17. Okay, so let's go ahead and finish up this practical exercise. Back to the midnight dumping site. I can't even remember the name of it now. It's been long enough since I read up on it. It didn't stick with me. It's a hazardous waste site, though. It's not one of Superfund's. It's not state Superfund or federal Superfund. So everybody got equal opportunity for their site to be presented. So as we looked at, we divided the plume into high, medium, and low. We do have the nearby sensitive receptors. We have an ORP of plus 200. Contaminant transport is 50 feet per year, which is nice, not going too fast. So, first question. Are there sensitive receptors at this site? And active treatment, therefore, is going to be needed. And what would the decision tree recommend based on your understanding of this presentation? And you do have a hard copy in your hand if you don't remember. I'll give you like 1 minute to consider. I gave you the answer earlier. I accidentally do that sometimes. Oh, Marilyn, I am jammed. I need your help for a second. I can't get it to go anymore. It won't go. Thank you. That's a good question. No. The question was, is it less than 50 feet from the red part to the stream? And the answer is no. It's more than 50 feet. Let's say it's 100 feet. And Marilyn, it still didn't do. I'm stuck at this slide for the moment. Did you get it to go down?
I hit the right and left.
Okay, that's where I want it. Right there. Okay, so now that y'all have heard my phone ring, who would like to volunteer to answer what they think the decision tree would recommend? And there's more than one right answer, by the way. So, volunteers. Marilyn's got a microphone. Okay, Keisha?
Okay, thermal.
In the red zone, thermal is definitely one thing that the decision tree would recommend. You could negotiate something else besides thermal. It could be another type of active remedy, but yes, thermal is one of the options. What about for the, let's see, I'm going the wrong way here. What about for the green zone? Ooh, I didn't give you that. Let's say 10 feet. Of course, close to the stream, it's not quite so much, the depth of groundwater. Well, let's do yellow next. Okay, red was easy. We know red needs to be treated quickly. Thermal is good. Closely spaced injection points would be good. Okay, yellow and green. So go ahead, Tim.
Okay, so in the yellow, you could do air sparging, and with 10 feet of separation, you could even potentially do SVE along with it.
So that's the correct answer. Anybody else have another idea? Like I said, there's not just one answer a lot of times with this. Okay, another idea would be ozone sparging. Another idea would be, let's go ahead and capture it with groundwater pump and treat, because we don't want any more to get in the creek. You don't have to do innovative technologies when a conventional technology, maybe again, that's sort of up to the facility and what they're willing to do, and if they want to install a pump and treat system. Some of them don't, but some of them might. So that would be another option. And yes, thermal could be considered in the red zone. Chemical oxidation could be looked at a distance from the creek, again, depending on your amendment longevity. At this site, you could do some type of Fenton's reagent. I wouldn't do it less than 50 feet from the creek, though. And I do think the air sparging or ozone sparging would be a good way to go. So that's sort of an example. All right. This is a real site. I know the name of this one. Like I said, I forgot the last one. This is one that was in State Superfund. Some people in the room may recognize it. I named it the Industrial Waste Pit Site. And red has over 1 million parts per billion TCE in it. So let's see what we got. Concentrations of TCE over 1,000 parts per million. Did you guys get this in your handout, by the way? Nope? Okay. So concentration over 1,000 parts per million. Travel time to surface water from the center of the plume is about 1 year. It's a year away from the core of the plume to surface water. It's a year. But the edge of the plume is pretty close to surface water. A reduced time frame is desired. pH, less than 6. ORP, greater than 100. Near source area. This is the site I was telling you about. The distal portions of the plume, ORP, less than negative 100. You have nitrate and sulfate. What do you think the decision tree would recommend for this, for these conditions? And you can separate the core from the distal part of the plume, if you would like. Let me go back. So the surface water body is actually on the left side of the plume. And you may see some blue diamonds. I don't know if you can see the blue diamonds from where you're sitting on the left side. I'll use a laser pointer and that might help you see them. The blue diamond right there. Those are surface water sampling points. And the distance from that point to that point is a couple hundred feet. It looks like the plume is heading this way.
Are there any residents in the area, or where's the public located?
There are no drinking water wells. The main receptor is the surface water body. Okay, let's go back to that. Nitrate and sulfate are present. We'll just assume they are above the criteria within the decision tree. Okay, did anybody have an approach for this plume? Tim, do you have an approach? No, this was Tim's side at one time.
Oh, wow. So we're probably looking at two different remedies. Obviously, you've got oxidizing conditions near the source.
Right.
Okay, so an injection, an ISCO injection could be helpful there. If you've got reducing conditions at the distal end, I take it that's closer to surface water. So you could try to augment those conditions and see if they'd still be effective.
So with the distal end, what technology did you say you would recommend?
I didn't. I really want to see what goes on if you do an ISCO injection. Is that going to deteriorate your reducing conditions with time?
Right. So it is a matter of understanding how the travel time within that plume. If you do that injection, is it going to be at your creek within, a year where you are trying to create reducing conditions? So it is something you really do have to understand the hydrogeology and travel times when you choose a technology. So the decision tree, the first thing it's going to say is, oh, you have DNAPL. Some of you may not know that that level of concentration is actually what you would expect for dense non-aqueous phase liquids to be present. Anything over 10% of the solubility is considered a potential for DNAPL. Some people use 5% or 1% in the groundwater, saying there could be DNAPL present, in which case you have to use your professional judgment when you're making a decision. The distal portion of the plume, zero valent iron with an amendment to improve longevity would be appropriate. Reductive dechlorination would not be recommended, which is the technology they tried to do out here. They were the ones that said, oh yes, we can change the pH of the aquifer, and they were not successful at that. And Tim remembers the days when they implemented thermal technology at this site. They did implement that in the area of highest contamination, which is an appropriate technology for such a level of contamination. Chemical oxidation is also viable for this site closer to the core of the plume. And the technology that they actually ended up with looks like this. They actually did thermal in the most contaminated areas. They did a line of chemical oxidation injection points in the middle of the plume, and there was enough distance between the middle of the plume and the distal end of the plume that they felt like the groundwater would recover and return back to its negative ORP, and that the chemical oxidation would not negatively affect the zero valent iron at a distance. So they actually did zero valent iron at the edge of the plume. And this one is broadcasting victory and success. It was in Angie Jones's shop. I don't know who's got it now, but very interesting monitoring reports showing that it really looks like they've got it taken care of now. So this is a great example of how you can do more than one technology, assuming you understand the hydrogeology of the site. So with that, I don't believe I have any more slides. Are there any final questions or comments or discussion points regarding this entire presentation?
Started reporting favorable results. How many years went by?
That technology was implemented, and within a year, they were seeing tremendous improvement. Now, just to sort of give you more history on that site, they did the thermal to begin with because they felt like they could get the bulk of it out. This facility was motivated because they wanted to abandoned the site. They wanted to sell it to somebody else. They had a buyer, so they really wanted to deal with this quickly. It was a company that they were highly motivated, which is wonderful to work with a company like that. So they went out there with thermal thinking they were going to get the bulk of the problem with thermal, and they did get quite a bit out of the ground, but the problem was there was another source area. This is not shown in the decision tree presentation, but there was actually another source area that they discovered because they had rebound and contamination started moving back into the area, and they realized they had an upgradient source area. And so as a result, the thermal did well, but it didn't get everything. And the plume still came back pretty significantly after that thermal event. So then they went to trying to find another remedy, and they came up with this. They initially said, we want to do reductive dechlorination. And I said, if you're in a hurry and you want to be out of here, that's not going to do something quickly for you. And they went and looked at the zero valent iron and the chemical oxidation. And they didn't get done in 5 years. That was their goal, to be done in 5 years, but they're close. They're making very good progress. And George Maloof is running around sharing that information. If you ever have a chance to hear him talk, it's the Hitachi site. And he will present the Hitachi site to you. I don't know who has it now. Reagan, is that yours? So I hope they're still doing well. They looked really good the last time I looked at them. So. Anything else? Jim?
Judy, this is about a collection of parameters. Do you think turbidity would have any influence on indicator parameters when you're collecting from either a monitor well or a geoprobe point?
I think turbidity is an issue for metals, for chlorinated solvents. Could the PCE absorb to dirt as it's floating around in the water? Maybe. But that should not be affecting things like DO and ORP.
So if you saw indicator parameter data coming from a geoprobe point with less than stellar turbidity, you wouldn't throw that out outright?
The only thing about coming from a direct push rig is that it's going to be exposed to the atmosphere. So I would not accept the ORP or DO data from a direct push rig because they don't have a flow-through cell. It's already been exposed to the atmosphere before you measure it.
Unless it could be drawn up and then sent to a flow-through closed cell.
Yeah, I don't see direct push rigs using flow-through cells as a general rule, but it'd be nice if they would.
Thanks.
First time I smiled. Anything else? All right, well, thank y'all so much for coming. I appreciate it, and hope you have a great rest of the day.